So we've looked at the basics of what a vector is and how to calculate components of a vector. What I'm going to do in this video, I'm going to talk to you about two specific properties that are vital in any definition of a vector, and that's magnitude and direction. Now that's the difference between a vector and a number. A number has a size, it has a magnitude. A vector has not only a size, but it's got a direction. It's pointing somewhere, it's going somewhere. We have to be able to calculate both of these. Now calculating the magnitude of a vector means calculating the size, i.e. the length of the vector. And there's a set formula we can use to calculate this, whether it's a two-dimensional or three-dimensional vector. When we're calculating the magnitude or the size of a vector, we can use this formula. So if I've got a vector AB, which has an x and a y direction here, I can calculate the magnitude of AB by doing the square root of x squared plus y squared. If I have a three-dimensional vector where I've got x, y and z components, I can calculate the magnitude by squaring all of them and then taking the square root. This is all based in the fundamentals of Pythagoras. The vector AB is the one that points between 2 points here, so a point A and a point B. Now whether this is 3 dimensions or 2 dimensions, you've got to remember to calculate the length of it, we have to figure how far along and then how far up this way. And that there leads us to a right-angled triangle, or Pythagoras, because x tells you how far along, so there's my x size, the y tells you how far up, there's my y, and I can calculate this length, i.e. the hypotenuse of this right-angled triangle, by doing x squared plus y squared and then taking the square root. So that's where the square root of x squared plus y squared comes from. This one here comes from a three-dimensional application. It's think back to National 5 work when you did 3D Pythagoras. If you were in a three-dimensional situation, so let's say a cube or a cuboid or some sort of a 3D box, and you wanted to know the distance from this point here to this point here, i.e. the space through the box there, you ended up having to calculate a third side because you didn't have a third side of this triangle, so it could be this side here going down this face, using Pythagoras, and then you had to use Pythagoras yet again to get this one, and that leads you to this formula right here for a 3D vector. So I'm going to show you a couple examples of this. I want to calculate the magnitude of each of these vectors here, so that should be a fairly straightforward calculation. Then this one is calculating a component of a vector from its magnitude, so a slight different variation on it. So the magnitude of the vector AB, what we know we need to do is, because it's a two-dimensional vector, it's just going to be x component squared plus the y component squared and then taking the square root of it. So that's going to equal the square root of 6 squared plus 8 squared. 6 squared, well 6 sixes are 36, 8 eights are 64, so it's 36 plus 64. It's the square root of 100, and I hope by now you could all do that. Square root of 100 is 10. So the length of the vector is 10 units. We don't have a set of units to use, so we just say it's 10 units. The magnitude of this vector C to D, well again, it follows the same formula. It's the square root of each component squared added together. So it's the square root of negative 1 squared plus 4 squared. Negative 1 squared is 1, 4 squared is 16. So that then gives you the square root of 17 units. We could just leave it as a surd there, and that'll be us fine with that. Take it to a 3D vector now, E to F, which has these three components here. Again, it's not different, it's not difficult, it's sticking with the same sort of formula. Except this time, instead of just minus 10 squared plus 0 squared for y, we've then also got a plus 4 squared for the z component. Our steps then remain the exact same. So negative 10 squared gives you 100, 0 squared is nothing, so we could just leave that off, plus the 4 squared is plus 16. So it's then equal to the square root of 116. Again, we can leave it in a surd form, simplify it as much as you can. You end up simplifying it down to 2 root 29. So calculating them, fairly straightforward. We can also do a reverse type of calculation. So if the magnitude of xy equals 25, we have to find the possible values of a. So I know xy is given by this, so what I know is the magnitude of xy is equal to the square root of this. So it's equal to the square root of 3 squared plus a squared. And I know that that's going to equal 25. So square root of 3 squared plus x squared is going to equal 25 in this case. Now we just have to work this through as a normal piece of algebra and solve. So to get rid of the root here, take the square of both sides and sort these bits here. So in here I get a squared plus 9 equals 25 squared. Well, 25 squared is 625. Slip the 9 across here and I get a squared equals 625, take away 9, which is 616. So I then know that a is going to equal the square root of 616. Now it says possible values of a. Remember, if we take the square root on this side, I could have a positive or a negative value. So if I take the square root of 616, what that gives me is positive or negative 24.8 to 1 decimal place. Okay, so calculating it like that, remember we could get two possible values, but again it's just working it back like a normal equation. So that's the magnitude, i.e. the size of the vector. What do I mean by the direction? Well, where the vector goes, that's the direction. So where it points, where it goes, that is the direction. So you can imagine I've got two vectors here, vector u and a vector v. The vector u goes this way and the arrow tells you which way it points, so it's pointing from left to right as I go up. The vector v is pointing from left to right as I go down. So these two vectors are telling you where they're going. Now what I can do is join them at the ends and then get a third vector. So I can join these two vectors at the end, so say I go up the way with u and then I come back here with v. What I can do is join these two ends of the vector there and get a straight journey between them. Now that journey there is given by the calculation of u and then the v. So it's given by u plus v. I've added the two together to complete the journey, and this is now a shorter way to complete it. This is also the case if you have to reverse vectors as well. So imagine I take this and I give you my vector u here now, but what I'm also telling you is that v points up that way this time from right to left. So it's going in the opposite direction. And imagine I wanted to do the same calculation. So I wanted to go up the u, but then I wanted to go from the end of u down to here. Now this vector u stays the same, but this one here is this vector v in reverse. So what I've done is taken the direction of u and flipped it. So it's now going to go that way. So instead of it being the vector v, it's actually now the vector negative v. So this one, I've gone up u, but now that I'm coming down this way, I'm actually going negative v in this case, because I've flipped the direction of the vector. Now this one here then means instead of u plus v like the last time, I end up going u minus v, because I'm going the opposite direction for this vector. Now this allows me to map journeys in any direction, because I know now that I can flip vectors to suit my needs. I just have to make sure that I take this into account with the vector name. So let's have a look at an example of this in a scenario I've set up for you. So I've got PQRS as a quadrilateral, and I've got a bunch of information here. Now the best bit of advice I can give you at this point is read the information and make sure you understand the situation. I know the line P to Q, the vector P to Q, is twice the side S to R in length. I also know that P to Q is U. What that means is then I can say, right, so if SR is half the length of that, I know then that SR is a half U. What I can also say is that P to S equals V, so this vector is V, and M down here is the midpoint of RQ. Now, I've got various vectors I want to find. Let's have a look. First, I want to find the vector S to R. Well, I got that from the information here. The vector S to R going along that way is given by this. So it's given by a half U. What I now want, second question, is the vector P to R. So I want the vector going between these 2 points there. Well, to do this journey, I've got to go up the V to S and then along from the S to R. So to do that, I've got to go up V, so I've got to do positive V, then I've got to add on the vector S to R, which I know is just a half U in this case. So there you go, P to R, V plus a half U. What I now want is S to Q. So I want the journey from S all the way over here to Q. Now, I could go from S to R and then R to Q. The only issue is I don't know what the vector R to Q is. However, I do also notice that I can go from S to P and then P to Q, and that will be my journey. So I could do that. Now, again, we've got to keep in mind the direction of the vectors. If I go from S to P, I'm going back the way in this vector here. So I've got to flip the vector around, flip the direction, flip the sign. So it's going to start with negative V. I'm going back the way in V, then I'm going along U, then I've got plus u. So there you go, my vector s to q is negative v plus u. If you prefer to get rid of the negative, you could write it as u minus v. Either version is acceptable. Then I want r to q, so I want this vector here, r to q. Well, again, to get from r to q, I'm going to have to go a journey I know. So I can go from r to p, then p to q, because I now know what the vector r to p is. I could also, if I wanted to, go r to s, s to p, p to q. So a slightly longer journey if I wanted to. But let's imagine we go r to p, then p to q. If I go r to p, it's going to be negative of this one. So it's going to be negative of the v plus a half u. I then add on this vector p to q, I add on the u. So now I've got the general way, I've got to simplify it all. Multiply out this bracket and I get negative v minus a half u plus u. Simplify it, and what I end up getting is negative v minus a half u plus u plus a half u. That there's my vector journey from r to q. What I now want is the vector p to m. M is the midpoint of r to q. So to get from p to m, I go p to q, then q to m. Now p to q is straightforward. I know it's u. I then want q to m. Well, I know that q to m is going to be given by the fact that m is the midpoint of the vector r to q. So I know that this is halfway along this vector. Now, I want to go from q to r, so I know the vector r to q here is this. So to do q to r, I've got to reverse the direction of it. So I'm then going to take away this vector here because I'm reversing the direction. But I'm also halving it because it's the midpoint. So I've got to take away half of the negative v plus a half u. So I've got all the components and the parts I need. It's now a case of simplifying it. So keep this vector here, the u. So I've got u, and then multiply out the whole thing. So I've got negative a half times negative v. So I've then got plus a half v. I've then got negative a half times a half u. I've then got minus a quarter u. And then it's a case of simplifying. U take away a quarter u, gives me 3/4 of the u plus a half of the v. So I've got my vector from p to m. We can use any of the direction vectors to create any journey as long as we bear this in mind. We have to look at the properties, we have to look at the direction and the relationship of the vectors to each other and follow a path. It helps to trace it along here sometimes and show the way you're going. That might just help your brain work along and visualize the scenario a bit better. Bear that in mind.